Okay. Yeah, welcome back to the lectures. So the topic of today is quantum electrodynamics, and I want to, basically I want to stress some important points which are already in the lecture notes, but I also would like to show you the same thing from a slightly different perspective. But first, as usual, let me ask you if you have any questions. Because then we can structure things a little bit. If there was anything unclear? Any questions? No? So the last lectures, you have noticed, obviously, all these were rather basic things. And I just wanted to set the scene for what's coming from now on. Basically, from now on, most of the time we will really deal with interactions which are from our present-day knowledge, which are realized in nature. And one of them is quantum electrodynamics. So one can hardly underestimate the importance of quantum electrodynamics. I mean, it really governs all phenomena which has to do with electricity and with magnetic effects. It's based on a classical level on Maxwell's theory, classical electrodynamics, and it involves the principle of quantization is relativistic in a sense, because actually already Maxwell's theory was relativistic concerning the description of electromagnetic fields. And quantum electrodynamics is the best tested theory ever. This is there are observables which were determined up to 10 digits accuracy, and also there are corresponding calculations in this framework of perturbative quantum electrodynamics which also reach that precision. So saying that, this means that quantum electrodynamics is extremely well tested, and actually its principles form the basis of developing also other quantum field theories. We will come to quantum chromodynamics, which is constructed very similar to quantum electrodynamics, and it is constructed in that way because that time one already knew that quantum electrodynamics is a very successful theory. Which of course would not, this is not a proof that then if you construct something similar is also as successful, but it turned out that also the strong interaction and also the weak interaction, they also give a good description of what we see in nature, at least on the level of collision experiments. There are also open questions, I already pointed that out, like dark matter and so on, which is not covered by the particle content of the standard model. Okay, so quantum electrodynamics is in a sense, concerning the ideas, the basis of the whole standard model. There, some concepts were developed which were then generalized to other theories. And the most fundamental principle which entered there is actually gauge invariance. Gauge invariance is something which was first observed in the Maxwell theory, and there it was more regarded as a mathematical issue, that constructed a theory which was based on the elementary, say, degrees of freedom were electric and magnetic field strength. And it turned out that one could describe them well, by obtaining them from a gauge, so-called gauge potential, a four-component object, and if you take specific derivatives, you get the electric and magnetic field strength. And then it turned out that there is some freedom to choose these gauge fields which do not influence the electric and magnetic fields. In other words, this is something which is unobservable, yeah, I mean, there's a freedom to choose these gauge fields, and this change, which is these possible changes which are connected to this freedom, they do not change any observables. Then, in the beginning, this was regarded as a, well, nice mathematical add-on, but it was not clear whether this had a deeper meaning. And the understanding that it has a deeper meaning only then came with quantum theory. However, in principle, one could also see on the level of classical electrodynamics that this gauge principle leads to something observable, to an observable consequence. And the observable consequence is that the photon is massless, which would mean in classical terms that the dispersion relation between the wave number of a photon and its frequency, that this is a linear relation, which means that there is no mass involved here. So one, at some point, one turned the argument around. One did not say, okay, we don't know why the photon is massless, so this comes somehow by chance, but if it is massless, classical electrodynamics has this symmetry concerning the gauge fields, but rather one turned it around and said, we demand this gauge invariance, and then as a consequence, if we demand that symmetry to hold for our theory, then the consequence is that the photon must be massless. But of course, phenomenologically, this was first based on observing that photons are massless, or in other words, that the exchange potential between two charges is of Coulomb type and not of Yukawa type. So it's long-ranged and not cut off somewhere. So this point of view changed to stressing more the symmetry character. And this is our modern understanding, that it's symmetries which tell us something about interactions and about the structure of a theory. And in this case, this is gauge invariant. So what I would like to do now is, while writing down once more what that actually means for the fields, and then I would like to add just one more principle, and then we try to write down the most general Lagrangian we can imagine, which includes electrons and photons. Based on the gauge principle, and one more thing which I will come to in a moment. Especially what I do not want to do is, I do not want to demand in the beginning that we have parity symmetry. So I want to show you that from rather general principles, sometimes one gets additional symmetry principles, which in a sense then come by chance. They are not enforced from the start, but they come out automatically because the theory does not allow anything else. Okay, I think this is a nice alternative way of viewing quantum electrodynamics. In the lecture notes I've done it in a different way. I've just said, okay, here is the Lagrangian. Believe it, it works very well concerning phenomenology. Now I want to do it a little bit differently, and actually the way I present it is also a slightly more modern point of view. And I will come to that in a moment. But let me first write down the basic things. Which are these here. So the gauge invariance is that L, so this is 4 of gauge covariance is about. So LQED, which is, let me stress that here, which I want to construct as a functional of fermion fields, which I call electrons, and photon fields. So these guys here, the type, psi bar, and a four-component object, a mu. So this here should be invariant with respect to the following transformations. If I change the phase of my fermion fields by a phase vector which depends on the position, and if I change accordingly my photon field, the electric charge. So this is just a convention, but let me keep it here and not in the transformation of the photon field. So I want this invariance to hold. And if I demand this automatically couples my photons to the fermions. There is no way out, because if I have a free Dirac equation for my fermion, then this free Dirac equation has a derivative somewhere acting on the, or say a free Dirac Lagrangian. There is somewhere a derivative acting on the fermions, and this derivative, when it acts on the modified fields, it picks up this phase here. And this I can compensate by this transformation property, but this means I have to involve the photon in addition. Just that the transformations between the fermion field and the photon field cancel. All this would not play a role if this is a global transformation here. So it's important that this is local here. If this is global, then d mu lambda would be 0, so the photon would not change, and the psi just gets a phase, constant phase. This has also a consequence. I mean, this is also discussed in the lecture notes. This with a constant lambda leads to a conserved charge by Noether's theorem. But this local property here, in addition, enforces that the photons are massless. Because I cannot write down a mass term for photons and at the same time satisfying this condition here. Okay, so the whole issue is that whenever one constructs derivatives acting on the fermions, it turns out that one needs these gauge covariant derivatives. And this I want to go through once, this is also in the lecture notes, but so this is an important issue that this I want to repeat here. Okay, so the point is to ensure this, we introduce a gauge covariant derivative. And this is defined by d mu, which contains the partial derivatives, and I have to look up the signs because there's some arbitrariness there, minus I-E. And u, then let's look at the transformation property of a derivative acting on a fermion field. So d mu psi, well, let me first write it down what it means. This is d mu minus I a mu acting on psi, and now under such a so-called gauge transformation, the fermion field is changed, and also the photon field is changed. So let's first plug in how the photon field changes. This is changed to A mu plus d mu lambda. And the fermion field changes to e to the I e lambda psi, and I don't write down the x dependence anymore, but it's assumed that all this depends on x. Okay, now we have to evaluate this. So this derivative acts now on the product here, so I obtain two terms. Whereas this here is just a derivative acting on lambda, so the whole thing is just a number which multiplies here my product of phase and psi. Okay, so now we evaluate this here with a product rule. So this is first of all a d mu, okay, acting on the exponential, I obtain a d mu lambda times I times e, these are constants here, times psi, which I will write down in the end. Then let me first pick up these terms, minus I e a mu, minus I e d mu lambda. All this multiplies the phase e to the I e lambda times psi, and I pick up one additional term, which is this derivative acting on psi. This is I e lambda d mu psi. And now, first of all, we observe what I already announced. This derivative of lambda coming from, well, the derivative acting on the modified psi field, which brings in addition this term, this drops against the modification of the photon field. So this here plus this is 0. And the rest I can nicely combine. So this is a phase, this I can commute with the photon field. And then the whole thing is given in the following way. So I first write down now this, then the photon field times psi. So this first term has cancelled that. This here is this, just writing the exponential in front, and this term here and this here. Now this here is again my so-called gauge covariant derivative. So this is e to the I e lambda d mu psi. So I have gained something including derivatives which transforms in the same way as the original psi field. Let's see whether I find that finding here. So the psi field just obtains the phase, and now my not a partial derivative acting on psi, this would be complicated, but this gauge covariant derivative acting on psi also just obtains a phase. Which means if I combine something with a psi dagger and a psi or a d mu psi, these things can be gauge invariant, because then these two phases cancel each other. Okay. This means the building blocks of a gauge invariant Lagrangian are, well, the field strength, the F mu nu, because this F mu nu also does not depend on d mu lambda. So this I leave to you to check that indeed this is the case. So this is gauge invariant. Let me add that here. And the other thing I can do is take a psi or a d mu psi and that psi bar. Then I can also take a d mu psi bar, which, okay, probably I should define that, which is meant to be a d mu psi dagger, and then multiplying that by gamma 0. Okay, fine. So the statement is, to rephrase that a little bit, do not use single A mu's, because they change in this non-homogeneous way. This forbids mass terms, for example, for the photon. It also forbids typically interactions between the photons, except if they are of special kind. I will come to that in a moment. But if I write down something like a mu, and the whole thing square, this would also not be gauge invariant. So one should not use the single gauge fields, but always appearing in these gauge covariant derivatives. And one should not use just partial derivatives, because they also create some trouble when they act on fermions. So the good building blocks are these here. This is now not a proof not a strict proof that one could not come up with something else, but actually this is the case. You cannot invent any structures not covered by that which lead to gauge invariant Lagrangians. Still, with this here, I could imagine to build infinitely many terms in my Lagrangian. Why is that? Well, for example, I could combine two F mu nu's. If I do that, first of all, this gives the ordinary Lagrangian for the Maxwell equation. But I can also take a square of that, or cube, or to the fourth power. And this causes specific interactions between photons. And they are gauge invariant because the F mu nu is gauge invariant, and I can construct it such that it's Lorentz invariant. I have not said that in the beginning, because I also want to preserve Lorentz invariant. So the governing principle of gauge invariance alone forbids several terms especially specific structures like mass terms for photons. And this is what we want because we have observed massless photons. So we want something which explains that. But it allows for arbitrary interactions. So I want to add something more here. And this has classically to do with renormalizability of the theory. Now this is something we did not talk about. Those of you who were in the quantum field theory course, they know this refers to whether one can make sense out of that theory as soon as one calculates loop corrections to whatever quantity. These loop corrections typically lead to infinite results, and one has to get to assign to these terms a well-defined meaning. And this is possible if one has a renormalizable theory. At least then this is possible. There are also cases, I come to that in a moment, where it's still possible for non-renormalizable theories to give a well-defined meaning to such terms. So I would like to add one more property to my Lagrangian, and then basically you're all welcome to make suggestions for terms which should show up in the Lagrangian. Okay, we will construct then the most general thing one can imagine. I will collect some more building blocks which can be useful, and then we just start out. So let me add a second principle, which is essentially renormalizability. We want that the coupling constants which show up, these are the coefficients in front of interaction terms, and we want that basically they are dimensionless. We do not want, in particular, that these coupling constants have a dimension which is 1 over mass, or 1 over mass square, or 1 over mass to 100. We do not want that these coupling constants have negative mass dimensions. Let me specify a little bit what that means, or let me tell you how this comes about. For this we first have to figure out what is actually the dimensionality of our fields. And what do we expect that a Lagrangian should look like, or the action should look like. The point there is, all that is based on a very simple principle. One obtains a Lagrangian by adding up a lot of terms. Adding up specific interactions, adding up the kinetic terms of our fields, adding up the mass terms if there are any. So one always adds up things. And as a completely general principle in physics, a completely general principle is you would not add up things which have different dimensionality. You do not add up something which has dimension of a mass with something which has a dimension of a length scale. We can add up things which by our natural units have the same dimensionality, because there we can adjust by choosing speed of light and h bar that this fits together. But there are things, but otherwise we do not add up things with different dimensionality, especially not, say, something which has dimension of mass with something which has dimension of mass squared. We never do that. This does not make any sense from a mathematical and physical point of view. Okay, but then we should learn what can we add up. So let me start with dimensionalities of fields. Well, first of all, let's start with the action. The action is the fundamental thing from which we derive equations of motion and so on. So what's the dimensionality of an action? Well, we know one thing which has the dimension of action, and this is h bar. H bar is the action quantum. And in our way of dealing with dimensions, we have put h bar to 1, which means h bar does not have a dimension. This means any action which we write down should not have any dimension. And this I write in the following way. Action. The dimensionality in powers of masses of S is 0, which means this is dimensionless. Then we come to our Lagrangian. The Lagrangian, well, is connected to the action by the fact that one integrates over space and time with the Lagrangian. So the action is integral e4x L. The dimensionality of length, any idea what that is in masses? It's the inverse of a mass. So we measure always, well, the same units have length and time on the one hand side, and on the other hand side, momentum, energy, but also frequency. So 1 over time is related to energy, or also 1 over length is related to momentum. And momentum and energy is also the same, energy, momentum, mass. So this here has mass dimension -1. Whereas, we also write this down, mass as, so that's how it is defined in a sense, by brackets. Mass is dimension +1, and therefore the dimensionality of L is, well, I have a product of 4 times inverse masses. To make the whole thing dimensionless, I need that L has mass dimension 4. Why do we do that? Well, because now from our kinetic terms, which are always there, we want to give some dynamics to our fields. These are what the kinetic terms are about, the derivatives acting on the fields, because part of these derivatives are time derivatives, and they tell us how things then change in time. From these, we can now read off the dimensionality of the fields themselves. So, from the kinetic terms, and let me write down the kinetic terms. One term for the Dirac fields is I psi bar d slash psi, and the other one are the kinetic terms for the gauge fields, for the photon fields, and this is f mu nu, f mu nu. These are terms in the Lagrangian. Now comes my one of the deepest physical principles: do not add up things with different dimensionalities. The whole thing here should have dimensionality 4. The gamma matrices in here are just number valued. They have nothing to do with the dimensions. They give a spinor structure, but I'm interested here only in the dimensions of the fields. So I have once this field, and I actually have it twice. By taking the complex conjugate, this does not change the dimensionality. I want to end up with a mass dimension 4. I have one derivative. A derivative is an inverse length. Or you can also say, in quantum mechanics, the derivative is related to a momentum. And if c is 1, the momentum is related to a mass. So this here has mass dimension 1, and the whole thing should have mass dimension 4. And I have two fields in here, which means the dimensionality of my field is 3/2. Okay, so 3/2 of this guy plus 3/2 of this guy, 3 plus 1 for this partial derivative is 4. And I want that this is a part of my Lagrangian. And similar way, f mu nu is part of my Lagrangian. The whole thing has dimensionality 4, so f mu nu has dimensionality 2. And therefore, the A mu has dimensionality 1 because f mu nu is related to the so-called gauge field, the photon fields, by having a derivative. This has mass dimension 1, and then this also must have mass dimension 1 to end up with mass dimension 2. First check whether this makes sense. Never add up things which have different dimensionalities. This here is a sum of two terms, so also they should fit together. This here has mass dimension 1, and this here has mass dimension 1. And that fits because the charge in natural units is dimensionless. Okay, so we have defined the dimensionalities of our basic fields. Now let's look at interaction terms. Let me take first one simple example. I just forget about photons and I want that my fermions interact with each other. So then I would write down something which involves more than two fermion fields. Okay, the first guess would be write down 3 fermion fields. But the whole thing, the whole term, there are some more properties now, not only that the dimensionality works out, but also the terms in the Lagrangian must be Lorentz invariant. If I couple 3 spin 1/2 fields together, it does not end up at spin 0. Because 3 spin 1/2 fields, the total spin, whatever it is, can be 3/2 or 1/2, but not 0. Odd number of non-integer spin fields does not yield something which is a scalar under rotations. And the rotational group is a subgroup of the Lorentz group. So I need at least 4 fields. So let's write it down. Simplest guess. I couple 2 fermions to something which is then also Hermitian, and I square it. That's possible, right? So what's the dimensionality of this? The dimensionality is, well, psi has dimensionality 3/2, psi bar also, so the whole thing has dimensionality 3, and I take the square, so this has dimensionality 6. And I have to end up with something which has dimensionality 4, which means I need a coefficient here. I can write down no arbitrary coefficients, but I want to analyze now what is the mass dimension of my coefficients. Well, this would be something with a dimensionless coefficient. Let me call that G. And I need some scale here, which has mass squared. And I want a G which is dimensional. Okay, so in principle, this is a possible interaction term for whatever theory you consider. So I have something dimensionless, I divide by a mass, I will say something about this mass in a moment. I divide by mass square, and I multiply with something which has dimensionality mass to the 6th power of any mass, and then the whole thing has dimensionality 4, as it should be. What you should see from that example is, of course, the more fields I put together here, the more dimensions of mass I need here in the denominator of this coefficient. Okay, if I want to couple 100 fermions, this goes with every of these fields has mass dimension 3/2, so 100 times 3/2 is 150. So I need a mass scale to the power of 150 in the denominator. Okay, now two things, two issues concerning such interactions. And what I say now is an old point of view from, say, 60 years ago, and a more modern point of view which was developed then in something like 50 years ago and further developed. The old point of view is like this. So, suppose we have a Lagrangian of QED. It turned out that when one starts calculating things, one picks up, when one calculates loop corrections to some observables, one picks up so-called divergences. And one can give a well-defined meaning to these divergences in a theory which does not have such coupling constants with negative mass dimensions. Coupling constants with negative mass dimensions always mess that up. Then one cannot give a well-defined meaning to what one has calculated. And the old understanding of that was, in a sense, I'm overdoing things now a little bit. Either we find a theory which is renormalizable, which does not have such coupling constants, and with which we can describe nature. This means nature is very nice to us. Or we cannot. Then we have to find something else, an alternative to quantum field theory, or maybe nature is so complicated that we have no clue how to deal with that. This is a little bit an unsatisfying point of view, I would say, from a physics philosophical point of view, because we do not want to depend on how nice nature is to us. Right? I mean, somehow we would like to understand something no matter how complicated nature is. Indeed, this point of view has changed, and the modern point of view is not so much is nature nice to us or not, but it has come to a quantitative point of view, how nice is nature. This is much better in physics, if you can quantify something. Maybe still then you have not understood why this is the case, but you have understood a little bit more than just this yes or no question. The modern point of view on, for example, quantum electrodynamics is like this. So let's forget about the other interactions for the moment. Let's suppose in our daily life and in our accelerators we only test quantum electrodynamics. There is still an issue. Quantum electrodynamics is renormalizable, that's great, but there is still an issue which I pointed out in our first meeting, and that is if one goes to very, very high energies, the coupling constant grows, and one does not know how to deal with that. Actually, it's not clear whether one can define the theory at very high energies. So this suggests that at high energies there is a different theory at work, different from quantum electrodynamics. This theory might be string theory, which means this might be a theory which is not a quantum field theory with local interactions, but something happening on a very, very small scale in a non-local way, but so cleverly designed that Lorentz invariance is not messed up and so on. can be string theory, or it can be another quantum field theory, or it can be something else, whatever. So it can be a theory which we are not sensitive to yet. Maybe we never will be sensitive to that. It can be at very, very high energies, which maybe we never resolve in any, neither in high precision experiments nor in our colliders, because at some point our resources are limited. So somewhere at high energies there is a theory which gives rise to quantum electrodynamics at the energy scale which we can access. What would such a theory do? Now the funny thing is, one can, independent of what such a theory looks like, one can write down something completely general, what this theory implies for lower energies. And basically one starts out at this, where the theory is still valid, and goes down in energy. What does that mean? Well, if I go down in energy, at some point I do not resolve the details of this high energy theory anymore. I just see its gross structures, I just see the smeared out structures. For example, if it was a string theory, I would not see the strings anymore. They would look like point objects to me. Then I'm at the level of a quantum field theory. Maybe I'm not at the level of quantum electrodynamics. I can be at a level of a completely general theory, for example, having such interaction terms. But the issue is that one can show that typically these dimensionful coupling constants, they pick up the scale where this deeper, better microscopic theory changes effectively to a quantum field theory. The scale where I can no longer resolve the intrinsic structures. In other words, if this here is at a scale which, well, now and in the near future we cannot resolve, this mass here would be very, very high. Extremely high, maybe. And this is now on the level how nice nature is. Not is nature nice or not, but how nice is it? If nature is very nice, quantum electrodynamics works over a large scale, which means such interactions have a mass scale which is very, very high. And if nature is not so nice, then this mass scale is not so high. If nature is very mean, then this mass scale can be on the level of the electrons, and then, well, then that's not really mean, because then we resolve anyway what's going on. Then we would have formulated a different theory right from the start. But as it is now, we see quantum electrodynamics, this is what phenomenology tells us, works over a large range of energies. It works from our daily experience of well, seeing light, down to chemistry, down to how atoms are built. Well, not further down, because then other interactions play a role, but from, well, daily life experience down to atomic scale, which are basically 10 orders of magnitude, QED works. So nature is extremely nice, actually. And from what we know nowadays, if one neglects all the other interactions except for quantum electrodynamics, I mean, quantum electrodynamics works everywhere. With the, well, if one adds, of course, the other interactions which we know of. So this scale, and this is now a statement about all coupling constants which are dimensionful, this scale seems to be very, very big. But if this scale is very big, the coefficient here in front of this interaction is very small. And it turns out that these interactions just do not matter. They are completely irrelevant. These interactions in a classical point of view would mess up renormalizability, but actually they are so small that they do not matter. If you multiply them within loops, still in practice this contribution is negligibly small. So they just do not matter. even if they are there at the energies which we resolve, they do not matter. And this is a more modern point of view than saying, well, we want renormalizable theories, we want theories without such coupling constant, because if we have them, we cannot deal with them. That's the old point of view. Either we have renormalizable theories, or we have to invent something completely different. The modern point of view is, it seems that renormalizable theories work because what would disturb the renormalizability comes with a scale which is very, very big. And therefore this is irrelevant. And then of course the next challenge at some point is to resolve that scale. But maybe it will take a while until we can do that. And if we resolve that, this is not the end then, but this gives rise then to a new theory. Because this scale is at the level where this new theory becomes visible. Not only by bringing in terms which are non-renormalizable, but also by bringing in new structures which at somewhat lower energies lead to such terms. So you have to distinguish in a sense three energy levels. One energy level where one has a deeper theory, more microscopic than, say, quantum electrodynamics. Below one regime where one does not resolve this microscopic theory, but where one still sees the influence of such terms. And then the really low energy regime where, well, of course one still doesn't, again, one cannot resolve the microscopic theory, but one is even so far away from this scale where this is relevant that also such interactions are irrelevant. Okay, so after this long introduction, let's take this here as a second principle, and after the break let's construct the most general Lagrangian we can think of, which is gauge invariant. So it contains, okay, there are now several conditions. A, I only want to have now these electron fields and the photons, not 10 other fields. B, of course, I want to have it Lorentz invariant. C, I want to have it gauge invariant, because this justifies why the photon is massless. And D, I want to throw out everything which has coefficients with negative mass dimension, like this one. And we will see that we just end up with quantum electrodynamics. Nothing more and nothing less. And there will be one particular issue, how actually parity invariance comes about. Okay, then I would say we make a break till 20 past 2.